In this lecture, we're going to discuss the mathematical tool which we'll be using in this chapter, and that is the scalar product. Now we know that we are here to examine the effect of a force over space, or what happens when you push an object with a force, and as a result, the object has made a displacement, delta r, or in an infinitesimally small amount, dr. What happens as a result of that? Now, for simplicity, let's not talk about the change in the direction of motion. Let's just talk about the change in speed, whether the thing is going to speed up or slow down. Now, clearly, as we saw earlier, in order to increase or decrease the speed, you must have a component of the force along the direction of motion, okay, parallel to the direction of motion or anti-parallel to the direction of motion. And that is, you do not consider the component of the force that's perpendicular to the direction of motion, because that is only responsible for the change in the direction of motion, not the change in speed. So if you're only interested in the change in speed, then if you look at this diagram here, as the object moves forward by a displacement dr under the influence of force F, the effect of this force can only be realized if it's got a component along the direction of dr. Now, the component of the force along the direction of dr is clearly F times cosine theta, right? So you get F times cosine theta, and this component, the greater this component is, the greater the change in speed. Also, the distance dr makes a difference as well. If you use the same force to push the object over a long distance, then of course it's going to accumulate a lot of speed. So it's a matter of taking the product of this component of the force and dr. Here dr is the magnitude of the displacement vector dr, right? So it makes sense to consider this product, F times cosine theta times dr. Now you realize that F originally is a vector, dr is originally also a vector, but what we're getting, this combination is no longer a vector, it's a scalar. And what you do is you take the magnitude of the vector F times the magnitude of vector dr, and then times cosine of the angle between them. So this combination is of interest to us. Now, those of you who have studied scalar product or dot product knows that what we're getting here is no other than the mathematical definition of a scalar product or dot product. The more general definition is when you have two vectors, in this case F and dr, we define F dot dr, that's the symbol of the scalar product, as a scalar whose magnitude equals that of the first vector df times that of the second vector dr times cosine of the angle between them. Okay. Now we see that this combination is of interest to us if we want to examine the effect of a force over displacement, over space. And in the more general notation, if I have two arbitrary vectors A and B, they both start from the same point, this point right here, the angle between them is theta, then we can define the so-called scalar product or dot product between these two vectors as follows. A dot B is defined as magnitude of A times the magnitude of D times cosine theta. Okay, so this is the definition. Clearly, what we're getting here is a scalar. That's why it's called a scalar product. And we use a symbol, the dot sign between these two vectors. So therefore, we also call it the dot product. So this is the mathematical definition. And we introduced this definition because we're going to use it in this chapter and a lot of other areas in physics and engineering. And I already gave you a hint why this is a desirable combination in our study of the effect of force over space. Now, we're going to certainly apply this mathematical tool to study the effect of force over space later in this chapter. But as far as this lecture is concerned, we're going to focus mostly on the math, on the mathematical aspect of the dot product. It is not just for applications in physics and engineering. The definition dot product carries important significance in mathematics itself. It can be used as a nifty tool to solve some math problems which cannot be easily solved with other means. So let me give you a couple examples to illustrate that point, okay? Example number one, suppose I have two three-dimensional vectors, okay? Three-dimensional vectors, and we're given the components of each vector. Vector A has a component, X component of 4 units, Y components of 8 units, and Z component of 10 units, and so on. And then the three components of vector B are 9, 2, and 7, okay? And given these components, of course, each vector is uniquely specified. You know exactly what that vector is, the orientation, the magnitude, and so on. Question is, can you find the angle theta between these two vectors? Okay, how would you find the angle theta between these two vectors? I mean, without our new tool of scalar product, how would you do that? We actually sort of did that in our discussion for chapter 3, and when we looked at the arc lengths between two cities on the surface of the Earth, right? So what we had to do was to find the vector connecting A and B. Okay, it's either A minus B or B minus A. We find the length of this vector, and then we use the law of cosine to find the angle theta. I mean, it's doable, but it's not all that straightforward. Turns out, if you use our new tool of scalar product, there is an easier way to get this angle theta in one step. Just one formula will take you there. Now, in general, I can write the vector A in component form AXI, AYJ, AZK, similar for B, BXI, BYJ, BZK. Now, suppose I take the dot product between these two vectors, A dot B, okay? I express each vector in component form, as I did. And then you got 3 terms in A and 3 terms in B, right? So you take these 3 terms in A dot, the 3 terms in B, how many terms are you gonna get in general? Well, it's gonna be 3 times 3, that will be 9 terms, right? Now, out of these 9 terms, look at, for example, the AX and BX. What you're getting is AXI dot BXI, right? AX, BX, these are just scalars. You can take them out first. And then what you're left with I dot I. What is I dot I equal to? Well, by definition, I dot I is the magnitude of I times the magnitude of I times cosine of the angle between I and itself. Of course, that angle is 0. So you get cosine 0, which is what? Which is 1. So I dot I equals 1 times 1 times 1, and that's just 1. Same thing can be said about J dot J and K dot K, of course. Okay? So let me write down these results. J dot J equal to 0. I'm sorry, equal to 1. And K dot K, same thing. Okay. And as a matter of fact, when two vectors are parallel to each other, you have the greatest dot product between them, because cosine theta equals to 1. Now, what about I dot J? I and J are perpendicular to each other. So you get a cosine 0, instead of cosine 0 degrees, you get cosine 90 degrees. That, of course, is 0. So any two vectors that are perpendicular to each other, their dot product is 0. I and J are no exception, and J and K is also equal to 0. J dot K equal to 0. I dot K equal to 0, and J dot K equal to 0. Okay? So you see, even though I have 9 terms, only 3 of these terms would survive. And that is I dot I, J dot J, and K dot K, corresponding to the product of AX, BX, AY, BY, and AZ, BZ, respectively, right? The other 6 terms, you got things like I dot J, J dot I dot K, K dot J, and so on. They're all 0. The other 6 terms are all 0 because you got the dot product of 2 mutually perpendicular vectors. Okay, so therefore, if you take A dot B, you're going to get only 3 surviving terms. You get AX, BX, right? That is for I dot I. And you get AY, BY, and that is for J dot J. And finally, you get AZ, BZ, and that's for K dot K. That's it. So we have found the expression, the value of A dot B in terms of the components of each vector. But on the other hand, we also know that A dot B is not equal to the magnitude of A times the magnitude of B times cosine theta, right? And if you're looking for theta, all I have to do is find cosine theta. So what is cosine theta to? Cosine theta equals A dot B divided by vector magnitude A times magnitude B. So you get cosine theta equals to A dot B divided by magnitude A times the magnitude B. I already know what A dot B is in its component form. All I have to do is divide this by A and B expressed in component forms. And that, of course, we all know how to do. So let me find a numerator first. Okay, let me find a numerator first. And that is AX BX plus AY. BY plus AZ BZ. And then it divided by the magnitude of A times the magnitude of B. Now the magnitude of A isn't that equal to the square root of AX squared plus AY squared plus AZ squared, right? And then followed by the magnitude of B, same story. That is BX squared plus BY squared plus BZ squared, right? So you see, as long as you give me these 6 numbers, AX, AY, AZ, BX, BY, BZ, I can find cosine theta, theta being the angle between the 2 vectors. And from that, I can find the angle theta itself. The trick here is to use the dot product to find A dot B first, and then divide it by the product of their magnitudes. Okay, so given the 6 numbers that we have here, AX equal to 4, AY equal to 8, AZ equal to 10, and so on, you can verify yourself that in our case, cosine theta is roughly equal to 0.7855, leading to the angle theta, which is roughly 38 degrees. Okay, so you can use that formula above for cosine theta, and in this one step, by plugging all the numbers in one step, we have found cosine theta. Then you can get theta with inverse cosine. It's just that simple. So that is one nifty way of finding a mathematical problem, solution to a mathematical problem using this new tool of dot product. Okay, and there are many other applications, but I was just going to talk about one more math application. Before we end this discussion, you will see plenty of other applications of dot product throughout our study of physics later. But this other sample problem about mathematical application of dot product is actually about a more famous law or theorem, and that is the law of cosine. Now, we all know the law of cosine. We studied them in high school. We studied the law of cosine in high school, right? Do you remember how they proved it? No, I can tell you, I don't remember in my high school days how they proved it. But even though if you're like anything like me, you probably don't remember how they proved it. But was it an easy proof? Okay, was it an easy proof that took like half a page? No, even though I don't remember exactly how they proved it, it wasn't something that straightforward. I mean, it's quite involved. Okay. Question is, what does that have to do with dot product? There are no vectors here, right? Well, here's the thing. I can turn this triangle into a vector triangle and try to use my knowledge of dot product. So you can prove this law of cosine in a much more simplified and elegant manner. Okay, now this in fact is an example of a general idea, and that is sometimes you're given only scalars. And it may not be a good idea. It generally is not a good idea to, to look at vectors if you have a scalar expression that you can replace, because in general, vectors are easier, scalars are easier to study than vectors. But there are exceptions to that rule. In some cases, you want to deliberately turn a scalar problem into a vector problem, because it turns out that the vector version of the problem is actually easier. And this is one such example. Okay, this is one such example. So let me show you how to do that. All right. So what I need to do is to first turn this triangle into a vector triangle. And that it's simplest thing to do. All I have to do is add 3 arrows. Because you get vector A, vector B, and then vector C. That's it. You have just turned into a scalar, a vector triangle. Don't forget these arrows on the top. All right, now what do I have? I know that C equals vector A plus vector B, right? That has nothing to do with the angle alpha. It can be any value. You always have that. Okay, but we're not interested in these vectors. We're interested in C squared, A squared, B squared, and so on. Can you express C squared in terms of dot product? Well, remember, if you take the dot product between 2 vectors, you will get the product of their magnitudes times cosine of the angle between them. What if these 2 vectors are the same vector? Okay, let's say both vectors are C. What is C dot C equal to? Isn't that the magnitude of the first vector C times the magnitude of the second vector C, right? That gives you C squared, times cosine of 0. And doesn't that give you C squared? So you see, I can get C squared with C dot C, right? And similarly, I can get A squared from A dot A, B squared from B dot B, and so on. So therefore, the way I start by proving to prove this law of cosine is to replace C squared with C dot C. So I'm going to do this. I'm going to do C squared. I'm going to do C dot C to replace C squared. Now we know C is equal to A plus B. So here is A plus B dot A plus B. Right? Now I'm counting how many steps I've used. The first step was to introduce a vector triangle C equals A plus B. That's the first step. Okay. The second step is to take C dot C as A dot B as A plus B dot A plus B. So that's the second step. We just done 2 steps. Now, similarly, and now next, C dot C, isn't that C squared, right? And that's what we have here. A dot B, sorry, A plus B dot A plus B. Isn't that A dot A plus B dot B plus B dot A and then plus A dot B, right? So what is A dot A? That's A squared. What is B dot B? That is B squared. And then you have 2 more terms, A dot B and B dot A. Now, does that make any difference if you put A ahead of B or B ahead of A in a dot product? No, according to the definition, it's just, the product of their magnitudes times cosine of the angle between them. The order does not matter, so they're really the same thing. So it's 2 A dot B, okay? Or 2 B dot A, doesn't matter. Look at how close we are already. This is the last expression. If you compare that with our target, which is the law of cosine right here. Let me highlight it. This law of cosine right here. We got C squared, we got A squared, we got B squared. You will have a 2 here in the last term, right? Now, it's just that we have to simplify this A dot B business a little bit. I can get rid of the dot product. So what is A dot B anyway? Some say, oh, I know what it is. That's AB cosine alpha. Huh? AB cosine alpha. Well, that will give you cosine alpha, which is desirable. It will give you the magnitude of A and the magnitude of B. That's also desirable. But there is one tiny little mistake. But you have to fix that. And that is, there's a negative sign in front of the 2AB cosine theta term in the real law of cosine. But here we have a positive term. Right? We have a positive sign. Right? Let me highlight this. Hold on. We have this is a positive, and over there in the target we're negative. So it looks like we proved it, or we missed a sign somewhere. What did we do wrong? Well, is it true that A dot B equals AB cosine alpha? No, it should be negative AB cosine alpha if we believe the law of cosine, right? Where does the negative sign come from? How come we missed the negative sign? Well, take a good look at the arrows A and B, okay? Here is vector A, here's vector B. Vector A ends where vector B starts, right? Which is this point right here. at the vertex of the angle alpha. This point is where vector A ends and vector B starts. Is that where, is that the same as we drew when we introduced the law, the definition of the scalar product? No, look at this point, this red dot here, okay? This red dot here, we define the angle theta with A and B both starting from the same red dot. Okay, from the same red dot. But over there, it's a different story. Over there, it's a different story. This point right here is where vector A where vector A ends and vector B starts. We don't want that. So what we want to do is we want to measure the angle between A and B where both vector A and B start. That's the vertex we'll be using, okay? So how do you do that? Simple enough, just move A, so it doesn't start from there, but rather it starts from here, okay? So let's do that. Let me move A now. Let me use a different color. After I moved A, I'm going to use the green color. So A has changed color from blue to green because I moved it from this corner to this corner. Okay, so let's do that. Let's change to green color and let's move A. Hold on. All right, so this is my new vector A. Now, can you see the angle between A and B? So this red dot is the common vertex where both vectors A and B begin. So by definition, this is the angle theta between vectors A and B when you do the dot product. So therefore, A dot B should be what? A B cosine of theta, not cosine of alpha. But wait a second, theta is pi minus alpha, isn't it? Okay, so I can write this as AB cosine pi minus alpha. Isn't that negative AB cosine alpha? That's where negative sign comes from, okay? So finally, I replace 2A dot B as negative AB cosine alpha, then I get C squared equals 2 A squared plus B squared minus 2AB cosine alpha. Wow, that is, as recognized, the law of cosine. That's the law of cosine right here. You can compare that with the one here. It's the same thing, okay? Isn't that wonderful? Look at how simple this derivation is. It took us really just half a page, right, with very little calculation. But it also helps us clarify in the definition of the dot product, what is that angle theta really defined? You know, it's not alpha, it's theta here. That's a little subtlety, but other than that, it's really, really, really simple. And it is the simplest and the most elegant way of proving the law of cosine as far as I know. And I hope you have seen the power of this new tool, the scalar product or dot product. And in the next lecture, we're going to apply this new tool to rewrite Newton's second law into a different form in order to solve problems that like you see in the first lecture. It'll become a piece of cake. We'll do that in our next lecture.